Okay, so in today's presentation, I'm going to go over how you run occupancy analyses in Mark, how you set up a design matrix, and how you include continuous covariates in your analysis. So we got a bunch of stuff that we're adding on here. So let's come over, get Mark started. We're going to open up a new uh, analysis here. So I want to come down to occupancy estimation, occupancy detection less than 1. Okay. And squirrel SQU 2019. This is the fall 2019 data. Let's open up the data set and take a look at it. Excuse me. And you can see at the top here is just some comments that kind of tell you about what the data set, what's in the data set. So squirrel occupancy fall 2019, we had 4 occasions, 1 group, and then we had covariates, and this is the order that the covariates are included in the data. So coming down here and looking at the first line of data, this first information in between these comments, the slash star, star slash, sets off just comment information. So this was 0.13, again, randomly chosen across the campus. And here are the data on number or whether or not squirrels are observed at that point during the 5-minute observation. In this case, no squirrels were observed. We have just one group, so group really isn't a part of this. In occupancy analysis, the point or the location where the data are being collected is the experimental unit. So if you did have grouping, you might have grouping by habitat. So if you had forested habitat and shrubland habitat, for instance, you might want to separate those for an occupancy analysis. So it's not individual animals like it is in the other analyses we've done. And then following that on the data line are the values for each of the covariates at that particular location. Okay. And again, those covariates are listed up here in order. So this first one, 10.75, was the average number of trees across the 4 visits. So again, we had 4 groups visiting each one of these sites, and they would estimate the number of trees over 2 meters. And there's some variation, as you might expect. So we just took the averages for all of these. So then the next is number of nut-bearing trees, 0.5. So 2 groups said there was 1, and 2 groups said there weren't any. So that's kind of shaky, right? Percent pavement. So everybody looks like gave it a pretty low value for pavement. Number of people. So at one point you just look and count all the people within that circle, again taking the average. Number of open trash cans, and then the number of closed trash cans. So no trash cans at this site. All right, then semicolon says, all right, that's it for that one, and you go on to the next. So that sets us up for the next step, which is entering the number of occasions. So we did 4 visits to these sites. There was just one attribute group, so no differentiation among groups, but we have 6 different individual covariates, and we want to name all of those. And you can't use spaces in the names here, so I'm just going to say trees, nut bearing. Then we come down to pavement, and that was basically any kind of man-made pavement within the circle. Number of people, and then open trash and closed. Okay. So that's good. We got that ready to go. And we can hit OK. It'll say pull it into this data file. And now let's take a look at the PIM matrices like we always do. And there's only one other one that we need to look at. Click on PIM matrix and then select all. And now I'm going to go to window tile so we can see them both. And you see you've got two different parameters here. You've got psi, which is occupancy for that point. And now notice we don't have psi 1, psi 2, psi 3, so on, because we are assuming that occupancy is closed. So either squirrels are present at a site and are all potentially visible or able to be detected, or squirrels are not present at that site. And so if squirrels are present, you could only detect them 1, 2, 3, or all 4 of the times that it was visited, and that's where we get our detection probability. If you look at the detection probability on the right here, so now we do have 4 potential detection probabilities. So each time that a group visited a site, you could estimate a different detection probability for those visits. Or like we've done before, you can just collapse them all and say, hey, is there just one overall detection probability between across all sites or all visits. Another thing I'll try is that there were 2 classes involved here. The first class visited each of their points twice, and that's where you get data set points 1 and 2, and then class the next day visited each one of those same points twice. So they would visit on those would be recorded in 3 and 4, and so there could be a difference by day or class or something. So it might be worth taking a look at that model to see if there's anything going on there. All right, so let's just go to our parameter index chart. And as usual, we have our blocks that indicate whether we're estimating a unique value for a particular parameter. So here is what we would call our most general model, where we allow detection probability to vary across the 4 periods. And of course, we just have one psi. So if we run this, that would be PT, okay, and then psi and dot, okay. So let's just go ahead and run that, say yes, we're going to use the identity matrix, and it'll put it into our model selection table, and there we go. Okay, so let's run another model. Let's just go to the chart, and let's just make P constant. That's a nice easy one to do. So I clicked on that rectangle for the P's, right-clicked and hit constant. Now I'm going to renumber with overlap. So we just have 2 parameters, P, constant across all visits, and psi. We can go ahead and run that model. So I'm going to call that P dot and psi dot. Okay to run. Yes. Identity matrix. Yes. Okay. And that does a good bit better, right? We got about almost 4 AIC units between the two. So basically it's saying that it's more likely that P is constant. Let's just take a look at these. So if we look at the estimates for P with the PT psi dot model, it's 21, 16, 30, 42. Okay, so indicating that there's some variation there certainly, but maybe not a huge amount. Okay. And if we look at the p dot psi dot, it's saying, okay, it's around 27%. Fair amount of variation around that, right? So some points they were really hitting it all the time, and other points they weren't. So let's try that one model I suggested where we're separating the first two from the second two. So we'll go to our PIM chart. Sorry. And, okay, we're still on one here. Let's make this time varying. I'm going to move this over to the right so that our P's are separate from our psi. And now what we want to do is hold down the control key, click on the second P, and move it over on top of the first. And then hold down the control key, click on that fourth P, and move it on top of the third. So now we're saying make detection probability for periods 1 and 2 the same, and detection probabilities for periods 3 and 4 the same. I'm going to renumber with overlap. Okay. Now let's run this current model. And I'm going to call this P day psi dot. Okay to run. Yes. Puts it up there. We might do better here. And yeah, that goes up to the top. Not by much. Not by much at all. Okay. But I don't know if you noticed that in the first time we looked at the P's, but it looks like detection probability was lower on that first day and went up, a fair amount on the second day. So maybe there was some weather factor that caused that. But anyway, let's stick with that P model. And now we're going to go into the design matrix and talk about, well, how do we set up those linear models that I talked about in the PowerPoint. Okay, so now we want to click on design, and we're going to click on reduced because we want to specify to mark exactly what kind of design matrix we want. And the first thing is the number of covariate columns. So that would be the number of variables that are included in that linear equation. So we know we've got 2 for the P's already because we're separating those for the 2 days. And then we have the slope and intercept for the correlation between, or the relationship between the psi, in this case we'll start out with psi, and whatever covariate we choose. All right, so we want to go up one column so that we have enough to handle all of that. And this is what we get for our design matrix. Okay, so notice we've got 2 rows here corresponding to our P1 and our P2. Okay, and we've got 2 columns associated with our psi. Okay, the third row is psi, and that's the one where we're going to, at least initially, include the covariates. Okay, so for setting up the design matrix for the P's, what we want to do is put a 1 in each one of those first rows, okay, and then a 1 in the next row, or the next column over, okay. And what this does is it sets like a baseline value for P, and then the 1 in the second column says, now let the P for day 2 differ from the P for day 1. Okay, so this is setting up sort of a dichotomous situation or estimation for P's. Um, and now for psi, again, you can think of these columns as like the elements in that um, regression equation. So our first one is going to be our intercept, and we would put a 1 there to estimate one value for y-intercept. And then we go over to the next column, right click, and come down to individual covariates. And here's where we get a listing of the individual covariates that we talked about. Okay, so we have trees, nut-bearing, pavement, people, open trash, and closed trash. Okay, I'm just gonna start off, show you the example of the correlation or the association with closed trash. That's the one that's probably least likely to be a top model. If the squirrels can't get into it, probably isn't affecting their occupancy, but who knows. So I want you to choose one of these other variables when you do it for your hypotheses. So we'll click that. So we've got everything set up now. So now we want to run, and we've got our P day, and what I'm going to do for psi is I'm just going to put psi closed to indicate that we're looking at the correlation with the closed trash cans. Click OK to run, append this to the matrix, and yeah, it drops down a fair amount here. Now let's take a look at the output that you get from this. If we look at the estimates of real parameters, again, it's going to give you your values for P for day 1 and P for day 2. And then it's going to give you an estimate for psi, but because we have all of these covariates that could be influencing things, we need to, when we estimate that, we have to come up with some values of those other covariates to make to come up with our estimate of psi. And you see here that this estimate of psi is based on these values for number of trees, nut-bearing, pavement, people, open and closed. Okay, so these are the averages across all of the sites that were visited, and that's often sort of a standard way for providing your estimate of psi across a whole study area like this. The other thing we can look at are the estimates of the betas. So we come one box to the left, and now we see that we have our estimates for our betas for P1 and P2. So those are just constants associated with detection probabilities on day 1 and day 2. The third beta is going to be the intercept for this relationship between number or occupancy by squirrels and number of closed trash cans. And this last beta is the slope of that relationship. And a couple of things you can see here. The beta value is very, very small, 0.007, so indicating, almost no change in occupancy as a result of change in number of closed trash cans. Really high standard error, and our confidence intervals going from minus 1.15 to plus 1.14. So again, a huge confidence interval that greatly includes 0. So again, we wouldn't really expect much. But the last thing I want to show you here is how you could plot this. So once you have your model selected with a continuous covariable that you're interested in plotting, you come up here to this plot, and it'll pop up and say individual covariate plot. Click on that, and now it'll bring up a box where you can select the parameter to plot. So we're going to have psi being plotted as a function of the number of closed trash cans. And it'll set up the axis. So the maximum at any one point was 5.5. Okay. Then you just click OK. And kind of as we expected, not much going on here. So that line is essentially flat, right? The red line is the plotted relationship between occupancy and number of closed trash cans. The green are the 95% confidence intervals. And notice that this is back transformed now. So this is going from 0 to 1. So this is the estimate of psi that we obtain by back transforming the logit function versus the number of closed trash cans, which is really what we're interested in. Okay, and I'd like you to include these plots for the variables that you choose in your homework that you hand in. So in order to do that, you want to save these plots as a JPEG. For some reason you can't save them as a clipboard. So save it to wherever you want to. I've got this practice mark session. You probably want to tell what the plot is, psi versus closed trash. Okay, could probably shorten that. And then that'll save that to that folder, just to give you an idea of what that will look like. So here it is, psi versus closed trash can, and you get the plot that we looked at. Okay, so you can then just pull that into a Word document by doing insert picture. Okay, so hopefully that gives you a good introduction to running a design matrix. One thing I want to show here, let's pull this up. So if you choose a model and then you click on retrieve, it'll automatically pull up that design matrix because it knows that you set up a design matrix as opposed to Mark using the identity matrix. Now, there's a lot of flexibility. Let's just stick with the same P model for everybody. But say you wanted to add another variable to your analysis, and I'd like you to do at least one model where you have two continuous covariates. Okay, so in order to do that, you just add a column. Okay, and it'll tack it to the end here. Notice that it also moves this over. I like to keep this grayed out column in between my P and my psi values because then it's easy to kind of remember. So then once you have that, you could come down here and like we did before, maybe you want to see if you add open trash cans to your model, if that might improve the fit. And so we could run that where we've got two covariates and closed, comma, open, and okay to run. Yes, and whoa, that one jumps up there. Okay, and a good bit higher. All right, so here's that situation. As far as the plots go, if you just turn in the plots of the single covariate model, so I want you to do 3 different individual covariates that you've thought about ahead of time and think, well, that might affect squirrel occupancy. Let's run that model. So justify why you chose the particular covariate in your intro to the lab, and then run the models associated with those covariates, run one more model associated with using two covariates, and then you'll be good. You'll have everything you need to finish the rest of the lab. All right. Hope that works. And again, we'll be around for folks next week when we're doing this lab if you have questions.